give a warm welcome to our guest presenter today, Dr. Barry Keim. Barry is professor and chair of the Department of Geography and Anthropology at LSU. He is also state climatologist of Louisiana. He is a PI on the Southern Climate Impacts Planning Program, or SCIPP, where he leads our coastal research and extreme rainfall work. He also leads the disaster science and management program at LSU. And he also, in his spare time, as you can see, so much spare time, he does consulting work for, he's done Hurricanes Katrina and Harvey, as well as a number of other precipitation extreme cases. And I think you can see from this why he never responds to my emails. He has a very full plate, but we're very fortunate to have him today during hurricane season to talk about hurricanes and storm surge and the changing climate, and some of the other work he's doing with SCIPP. I'd like to also mention that his research involves climate extremes, especially heavy rainfall and hurricanes. He looks at detection of climate change and its impacts, and especially statistical analysis of extremes, which includes probable maximum precipitation, which I think he's going to talk a little bit about today. Barry is born and raised from Louisiana, grew up in Chalmette, near New Orleans, and he did leave Louisiana for a brief few years where he served as New Hampshire state climatologist. I know that he really misses the winters up in New Hampshire, and I've heard that if LSU cancels their football seasons, he's threatened to move back to New Hampshire. So with that, we'll let Barry take it away.
Yeah, I call New Hampshire purgatory, if that tells you anything about what that experience was like. Well, thanks for the invitation to be here, Mark. That introduction was made way more than I deserve, and probably way more than anybody actually wanted to hear. But nevertheless, I'm going to talk about hurricane storm surge and the changing climate, and I'll just throw in a smattering of other SCIPP projects. And as you can see, for those of you, I assume most of you may know what SCIPP is, but it's a Southern Climate Impacts Planning Program. It's this kind of a joint venture, primarily between Oklahoma and LSU, but there's some other entities involved as well. And a lot of the stuff I'm going to show you kind of stems from research that we've done out of SCIPP. So with that as prelude, I'm trying to advance my slides and they're not advancing. So let's try something else. There we go. So as state climatologists, I mean, you guys have your Gary McManus over in Oklahoma, and your other states, I'm sure, have your state climatologist in some office somewhere. And what we're all charged with is provision of climate data. I provide data to lawyers, the Department of Environmental Quality, State Attorney General's Office, State Police, and I also provide data to second and third graders. And I hold those second and third graders in as high regard as I do the lawyers. I also am charged with monitoring the state's climate in terms of impacts, doing things with the drought monitor, for example. I'm also charged with educating the state. This involves a lot of it is media interviews. I do anywhere from 100 to 200 media interviews a year. In fact, I was actually on with the BBC about 45 minutes ago. They've had some issues there, and somehow I'm on their Rolodex, so they looked me up. And then also fostering and conducting climatic research, some of which I'm going to show you in just a minute. You know, as state climatologist, called in to give talks quite frequently on climate change. This is pretty much what that feels like, to give you some idea. Again, working with drought with the National Drought Mitigation Center, although I have to admit that for the last year or so, I've been doing a lot of delegating in this regard as other responsibilities have usurped my time. But with that, I'm going to go ahead and start in on hurricanes. And I always like to begin this discussion talking about population statistics of all things. And what this is something that came out of a book I co-authored with my old PhD advisor about 10 years ago. And then Vinnie Brown and I, some of you may know Vinnie, just updated this for another paper. But this is the population of the U.S. coastal counties and parishes. We don't have counties in Louisiana. We call them parishes, all around the Gulf of Mexico. So it's just the parishes and counties that immediately surround the Gulf. And bazillion numbers here. Don't want to get lost in the numbers so much, but in the year 1900, I'll use my cursor here, in the year 1900, in all those coastal counties and parishes, there were less than 1 million people, which is kind of mind-blowing to me. By 1950, 50 years later, this jumps up fourfold to 3.7 million. By the year 2000, it's up to 12.4 million. The 2019 census has us at 16 million people. Now, we can get the people out of harm's way when hurricanes roll up on our coast, but what we can't get out of harm's way is the oil and gas infrastructure, the yacht clubs, the McMansions, the hotels along the Florida beaches and Alabama beaches, for example. So when those storms roll up, the consequences are still incredibly catastrophic. And we'll talk a little bit about that as we waltz our way through this. But these population statistics going from less than 1 million in 1900 to over 16 million, 16 times the population, just a little over 100 years later that's a lot of population growth and a lot of issues to deal with. So I'm going to begin here with a Rorschach test, but not seriously. What we have here is my time-space continuum of hurricanes in the U.S. and in Mexico along the Gulf Coast. So this is kind of taking an Einstein approach, merging time with space. So what we have is time on your y-axis starting at 1901 from the top, and I have this through, I believe, the 2017 season. And then on your x-axis, label across the top is geography. It's a series of locations. So we're looking at about 70 or 75 individual time series, all organized geographically, going from the Yucatan on the far left, going clockwise around the Gulf of Mexico into Texas, Louisiana, the north central Gulf Coast, all the way down to Key West. And then we go up the East Coast from Miami on into the mid-Atlantic and eventually on into New England. And anywhere you see a little green dot, that represents a tropical storm strike. Anywhere you see a yellow dash, you're looking at a hurricane category 1 or 2. And anywhere you see a red dash, you're looking at a category 3, 4, or 5 hurricane, a major hurricane strike at that location. So just want to draw your attention to a few things. For one thing, the area south of the Bay of Campeche, not very few storms. Here is sort of the mother lode of storms. We're looking at the late 1920s, 30s, and 1940s. The geographical breadth here is South Florida. So that area was just absolutely hammered, annihilated, if you will, in that stretch of years. Then in the 1950s, the center of gravity shifts over here into the Carolinas, then back over here to South Florida in the early 1960s. Then we go into kind of a relative period of calm for about 30 years, from the mid-60s to the mid-1990s. Then activity starts picking up here in the the north central Gulf Coast, as well as in the Carolinas. And you can very clearly see the years 2004 and 2005, which were notorious with the number of storms and the number of landfalling storms, and the entire north central Gulf Coast from about Galveston all the way on down to, in fact, really all the way down to St. Petersburg and the Tampa area were hit very, very hard. There's really hardly a piece of that coast that wasn't inundated with a major storm surge. So the big question is, well, why this active period, and then why a relatively quiet period and then active again? Well, the best explanation really is the Atlantic multi-decadal oscillation, which is just a very fancy index.
You are voting for election.
Just a very fancy index for the sea surface temperatures across the North Atlantic Basin. And that period from the mid-1920s to the mid-1960s, the sea surface temperatures were primarily running above normal. Then in the mid-60s to the mid-90s, the sea surface temperatures were cooler than normal, and we didn't get quite so many storms. We did get some bad ones in there. The frequency wasn't really there, but didn't match this other period. And then since 95, that's, for whatever reason, that switch flicked back in the other direction. The sea surface temperatures have been running warm again. They've been running warm since 1995. They're still running warm. And of course, in most years since 95 have been hyperactive with a couple of El Nino year exceptions. And of course, this year, we're already out the gate at a record pace, by the way. In fact, we're on pace to even beat the 2005 season in terms of the total number of storms. We're ahead of schedule, even at this juncture. So clearly, we're in a warm mode right now, and until that changes, we can just assume that every year is going to be hyperactive. for the foreseeable future. There's a lot of discussion about climate change and what are the impacts on hurricanes. Now, just for full disclosure, this is some work that was originally done by Bill Gray and his team at Colorado State, kind of addressing some of this this issue. And basically, they compare two 25-year periods, 1945 to 69, which was a period when the sea surface temperatures were warm, but global temperatures, this is the global temperature curve, global temperatures were much cooler than they are in more modern times. And comparing that with the subsequent 25 years when the sea surface temperatures were cool, but that the global temperatures were on this dramatic upswing. And you can see all the category 3, 4, and 5 strikes between these two periods. So this period here, we have warm sea surface temperatures, but cool global temperatures. And there are all your major hurricanes. And then here we have warm global temperatures, but cool sea surface temperatures, and not so many storms. So I think the take home from this is that, this is not to say that the global temperatures don't mean anything, but that the sea surface temperatures are a much stronger controlling factor and indicator of what the severe hurricane climatology is ultimately going to look like. And this is just a little geography of that previous time-space continuum. Just forget about all the big charts at the top. Let's just look at the larger one down on the bottom. Just shows you this geography again, going from the Yucatan to the left, going all the way around the Gulf of Mexico till we hit Key West, go up the East Coast all the way to Eastport, Maine. And you can see the total counts of tropical storms, hurricanes, and then major hurricanes in red. The most active spot on the coastline is Cape Hatteras, North Carolina, in terms of total tropical activity, which you can very clearly see over here in South Florida, just how active it is with hurricanes and major hurricanes relative to tropical storms. And then over our way along the Gulf Coast, the most active spot is Morgan City, Louisiana, in terms of the sites that we actually analyzed. And then we also took those data and did a return frequency analysis. This inner swath, the one closest to the coastline, is telling us what is their average return frequency for all named storms, all tropical systems. And you can see it's about once every 3 to 4 years, any given location can expect a strike, if you will, by a storm. Cape Hatteras and the Outer Banks of North Carolina, notice it's once every other year, demonstrating that very high frequency of storm activity in this neck of the woods. Hurricane activity is in the middle swath, so this is all hurricanes. And in Louisiana, about every 8 to 10 years or so. Down in South Florida, every say 4 to 5 years, they get a major hurricane. About every 5 years by the Outer Banks of North Carolina. Major hurricane activity is really interesting in terms of the geography. In Louisiana, I would say every 20 to 30 or so years. Notice this area in the Big Bend of Florida is 105 and 105 pluses. These are places that have either been only hit once or not at all in an entire 105-year climatology that we looked at. And then also, this was a big surprise to me. Northern Florida, starting with Cocoa Beach, Florida, going north up into Jacksonville and into Georgia. Notice all these 105s, 105 pluses. These are places that have not been hit by a major hurricane or only once been hit by a major hurricane in the whole 105-year record. So if storm surge is what I'm really worried about and major hurricane damage, it makes a whole lot more sense to be in Jacksonville than down at South Beach. So these kind of return periods can certainly have a lot of applications in planning for these kinds of disasters. Now, in terms of our hurricane records, I'm sure most of you realize it's inhomogeneous because of the way we do observations. And in fact, as you go back in time, if you go back to the early 1900s, for example, we were primarily looking at land observations. Our landfall record's probably pretty good, but the data from offshore is not very good. And we were dependent on ship observations and ship logs to try to piece together what that hurricane history looks like. Obviously has some very severe limitations. Once we get into about the mid-1940s, let's say, right after World War II, our records get dramatically better due to aircraft. We had a lot of technological innovation in aircraft during World War II. So post World War II, we were able to use and implement some of that technology into surveillance and observation of hurricanes. So our records make a dramatic jump upward in quality starting in the mid-1940s. And then, of course, once geostationary satellites go up and polar orbiting satellites, our record gets really good, starting in the late 60s or around 1970-ish, if you will. So record pretty sparse, especially offshore, in the earlier part of the 20th century. Gets gets better with the aircraft starting around 1945, and then gets, I would argue, really good where we barely miss anything around the late 1960s or around 1970 or so. And this just shows you the importance of satellites. I mean, here we are looking at, this is one day, September 26, 1998. We had 4 hurricanes going at the same time. We had George entering the Gulf, we had Carl, Ivan, and Jean out in the Atlantic. Now, if we were dependent on ship logs and they were all reporting something out in the Atlantic, we probably would have assumed all 3 of these storms were just one storm. And that's assuming we would have had any record of it at all, even to begin with. So this just shows you how important satellites have become in this field. This is some work by Christopher Lancy demonstrating just how inhomogeneous our records are. This is a classic paper that was this was published in one of the AGU publications, and what he's showing here, this is the ratio of the number of storms that made landfall versus the number of storms that stayed exclusively out over the ocean. And if you look at this record, in the earlier part of the century, this ratio changes dramatically. And once we get into the aircraft part of the record, you notice a big jump in the number of storms that we actually know about out over the oceans. And then it becomes even more imbalanced, if you will, where we know a lot more about non-landfalling storms with the satellites, and the record gets quite a bit better. But if you notice down on the, and underneath, what this shows is the percentage of storms that strike land in our record. So notice all these years where all these bars go all the way to the top, we only know about storms that made landfall in those given years. And then once we get into the satellite era, notice the change in how that climatology plays out. Bottom line is, there's a lot of storms that, that we're missing back in the earlier portion of this data set, especially ones that stayed exclusively out over the water. And this is just another example of how this plays out. This is comparing the 2 busiest hurricane seasons on record. Hopefully 2020 won't break the 2005 record, but we'll see. But you can just see, the number of storm tracks and storms that we had that played out in the middle of the Atlantic Ocean in 2005. And this is what we know about that played out over that same area in 1933, which was the previous record holding year for the total number of storms. It's just a dearth of storms out over the depths of the Atlantic. So surge is the biggest problem with hurricanes. This is where most people die. They end up drowning in a storm surge. And here we could just comparing and contrasting Galveston of 1900 with Hurricane Ike in 2008. And even despite over a century worth of technology in the field of meteorology and so on, we can get the people now out of harm's way. In Galveston, about 8,000 people drowned. Certainly, we didn't have that kind of mass catastrophe in terms of human life in Hurricane Ike, but you can see that the landscape doesn't look a whole lot better. It's not a significant improvement on this. This is the Bolivar Peninsula in Texas that was basically swept clean by the storm surge from Hurricane Ike. Here's another example of the Richelieu apartments in Florida. Excuse me, not in Florida, along the Mississippi Gulf Coast. And this was before a 24 to 25 foot storm surge came roaring through with Hurricane Camille. This is where a supposed hurricane party played out. There's a lot of debate on whether that actually happened or not. But nevertheless, you still can see the damage that was inflicted on this structure from that 24 to 25 foot storm surge. So we, as part of SCIPP, put together a database called SURGEDAT, stands for Surge Data. And it's the world's most comprehensive storm surge database. This is, again, obviously a joint venture between us and Oklahoma as part of our SCIPP project. And just to give you a couple of examples of what this looks like, we have search tools. This is, you can pull up an individual storm. This is Hurricane Ike. And every one of these little dots represents a surge observation at that location. So we can really do some interesting things with mapping storm surge for individual storms. And you can click on any one of these any of these little buttons, if you will, and you can get the actual storm tide or storm surge at that given location. And we also have a search by location tool, where in this case I just click down on the Port of Houston, put a 25-mile radius around it, and what the tool will do is pull up the single largest storm surge that appears within that circle for all the storms that have at least one observation within that radius. So we basically can build a time series and a storm surge history for a location just by pointing and clicking on the graphic. And with that, I've been able to put together with our database, put together the top 10 highest surges along the US Gulf Coast. I probably could have told you the top two with Katrina and Camille, as a lot is known about those two storms at 28 and 24.6 feet. And then we have, all of the rest, which I never could have told you, with Carla, with a 22-foot surge in 1961, and so on down the line. This tool has enabled us to actually interrogate these surge data, and our SURGEDAT database is like a clearinghouse for all surge information. And we're still putting improvements in it. We have datum issues that we're trying to correct for, and eventually we're going to have this thing all smoothed out and make it available to the general public. I also put together a top 20 surges for Louisiana, and interestingly, Katrina and Rita come in number 1 and number 2. They occurred 4 weeks apart in 2005, which needless to say put a lot of stress on the state in terms of its economy. I mean, the state was really ravaged in that particular year, and we're still recovering from those two storms of that single year, and for obvious reasons. We're also working on a project to analyze storm surge return frequencies by location. And we did this for 26 locations around the Gulf. This is kind of a preliminary study. We're not really happy with some of the methods that we're using. We're trying to get a little more sophisticated. So this is an unfinished product, but it still has revealed some interesting things about how much variability there is in surge values across the Gulf Basin. So what you're looking at, if just take any location in particular, here we're looking at site 16, which is Bay St. Louis, Mississippi. We're looking at the 500-year, 200, 100, 50, 25, and 10-year return frequencies as you work your way down the bar. And then these red dots actually represent the storm surge history for that location from which those statistics are derived from. And as you can see, Bay St. Louis has the highest frequencies for any given return period. It's a unique area, given this little nook, if you will, created by the delta of the Mississippi River in New Orleans. In a southeast wind, that water kind of gets funneled up into this area, and then it gets refunneled into another little bay on the coast of Mississippi, which really exacerbates those particular storm surges. What's interesting to me is we look at Bay St. Louis and compare it to site number 9, which is Morgan City, and the return frequencies. I mean, the estimated storm surge for a given return frequency just pales in comparison, coming in about at less than half of what the surge would be for a 500-year event. So there's just tremendous variability along the coastline, given all the nuances that go into ultimately producing those surge values. We've also taken our database globally. This just looks at the surges all around the world that are in our database. We kind of did this to just kind of measure up Gulf surges versus other basins and how do they stack up. What we found is that the Gulf is very similar to Australia in terms of the magnitude and the frequency of the storms, but the surges that take the cake actually are in the Bay of Bengal, whereby they don't get quite as many as we get, but the ones they get are truly catastrophic or can be catastrophic. And the largest credible surge in our database was from 1876 from Bangladesh at 44.9 feet. So just think about that for a minute. And that's a lot of storm surge. And the largest surge in the Western Hemisphere that we know about is Katrina at 28 feet. So obviously that pales in comparison to what can play out in Bangladesh. You notice we have 2 surges in India that are upwards of 40 feet as well. Just give you a few slides here of what the damage can look like. This is my hometown of Chalmette, Louisiana, in St. Bernard Parish, just downriver from the city of New Orleans. And this is in the throes of Hurricane Katrina surge. My wife actually went to this high school right here. That's also 2 stories, so you see the 2nd story poking up out of the floodwaters. I lived about 2 blocks off the left edge of the photograph. This is actually the house I grew up in here, a 2-story. The 1st floor is completely underwater. Here are our neighbors' homes, all water up to the rafters. This is kind of the aftermath after they gutted the house I grew up in. This is a house that actually popped up like a cork. The water came up so fast in this area that the water didn't have enough time to penetrate into the house, and this popped up with its concrete foundation on it and floated down the street. And I was told by the neighbor who took the picture of my house that basically it went from no water on the ground to about 10 feet of water on the ground in about a half an hour, to show you how fast that happened. So there wasn't a whole lot of time to get yourself prepared. This is in the lower 9th Ward in New Orleans. One of these shotgun houses picked up off its foundation, floated some distance, and is laying down in the middle of the street. This is also in the lower 9th Ward. You can just see the utter destruction in the background. But I want you to notice the proximity of this barge and bus. This picture was taken about 2 weeks after Katrina hit. I actually finally made it out there about 6 weeks after Katrina hit, and this is what I found. So I want you to notice the juxtaposition, obviously, of the barge and the bus. Okay, here we have some tens of feet that separate them, and in this case, this actually occurred after Hurricane Rita made landfall about 200 miles or 250 miles down the Louisiana coast, actually at the Louisiana-Texas border. And obviously the flood walls, this flood wall that you see in the background here, a lot of this was breached, and the flood waters were obviously so high in the same area enough to resuspend this barge and lay it down on top of that bus. And that's an aspect of flooding. I mean, I guess it didn't matter much. There really wasn't anybody back to those houses yet anyway. But nobody really talks about the 2nd flood that hit New Orleans post-Katrina. And it's just some more of the sensational things that took place. Every block had something for the highlight reel. So some of the other projects that we worked on using our surge database, we worked extensively with folks trying to understand something called the Ike Dike. We worked with Rice University and Texas A&M at Galveston, where there are a couple of proposed seawalls that they were trying to put in to try to protect Galveston Bay as well as the Houston Ship Channel. And some of these were pretty far-fetched ideas, like a 70-mile long surge barrier along the coast here to protect Galveston and Galveston Bay. I don't quite know where this is now. We've been away from this project for a couple of years now, but there's probably still some wrangling going on. If anybody knows about what the outcome of this is, I'd love to hear it. Some other work we've done, this is probable maximum precipitation work. This is some work we've done with a private consulting agency called Applied Weather Associates. We've subsequently published a couple of papers out of some of this research. And what we're looking at here is, well, what probable maximum precipitation is, just to sort of define it, it's the upper capacity of the atmosphere to produce rainfall. So it's basically taking every worst case variable, putting it together. It's got to be meteorologically possible. Probably has either not happened or only happened in a couple of locations across the region. But if you put all those variables together, how bad could that rain be if that did indeed occur? And these numbers that we're looking at here are for a 10 square mile area for a 72-hour duration. Down here in South Louisiana, we're looking at numbers in the, sort of between 45 and 50 inches of rain could potentially be produced, we believe, over a 72-hour period. And some of the guidance for this comes from Hurricane Harvey. And this is the rain from Harvey. This is the total spatial component. We took this information and put it into what we call a DAD, a depth area duration table. And over a 35,000 square mile area over 5 days, 120 hours, we had 22.5 inches. That's an area about the size of South Carolina. So think about taking South Carolina and putting 22.5 inches across the entire state in 5 days. Also, over a 2,000 square mile area, we had 42 inches. That's about the size of the state of Delaware. So again, over 5 days, think about putting 42 inches of rain over Delaware in 5 days. And that's what happened in Hurricane Harvey across the greater Houston, Beaumont area. And the storm was truly catastrophic. It's got to be, in terms of the total volume of water produced, I can't imagine there being another storm that's even going to come close to this one. And we're trying to figure that out. That's a project that's ongoing as one of our SCIPP projects, is to try to see just where does this storm rank. Because we know there are point rainfall totals that come close, like in Hawaii has at least a place that has roughly 60 inches of rain, whereby we had 2 locations in this event that had over 60 inches of rain. Comparable point rainfall totals, but in terms of the total volume and area impacted, I don't think anything's going to come close to touching this one. We also had a big storm in August in 2016 in South Central Louisiana, including Baton Rouge. And all those areas in purple, these purple bullseyes, are like 20 to 25 or even 30 inches of rain in those locations. Some of the return frequency analysis we've done, all these areas in this deep red are greater than a 1,000-year event in terms of the rainfall totals over a 72-hour duration. And just a little smattering of some other projects that we had ongoing to put some of this in a climate change context. This is some work done by Emily Powell, one of my PhD students. And we were looking at, for example, summer afternoon temperatures greater than 95 degrees. We're looking at trends. And all these areas across the southeastern US with the large graduated blue circles have highly significant trends toward decreasing 95-degree days. So the maximum temperatures seem to have a declining trend across the region, whereby when we looked at the minimum temperatures, what we call tropical nights, where temperatures greater than or equal to 75 degrees, all these ones with the large red graduated circles have increasing trends of minimum temperatures greater than 75. So bottom line is the high temperatures are coming down, minimum temperatures are going up, okay? And when we looked at the diurnal range of temperatures across the region, all these areas with the large graduated blue circles on the bottom down here have a declining diurnal temperature range over time from 1948 to 2012. So those are some interesting results. So while your overall temperatures may not be changing a whole bunch across the Southeast, there are some temperature nuances that are taking place that are very interesting and have serious implications. I mean, I know the agricultural folks are incredibly unhappy when the temperatures don't drop below 75. That's important in that phenological cycle. And it's not an insignificant result. And then also we looked at, this is also some of Emily Powell's work, whereby she found the daily intensity of rain going up. All the stations with the large green graduated circles are showing increases in what we call a simple daily intensity index. So so rainfall, the intensity does seem to be going up. We took that a step further with a subsequent study. This is some work by Vinnie Brown, another one of my PhD students, and we have about 4 papers actually published around this general topic. But just to cut to the chase, what we found was that hourly rainfall intensity is going up, which is indicated by all these upward green arrows. And then on the bottom chart, B, is all the ones that have downward arrows indicate that the storm durations are getting shorter with time significantly. So we have significant increases in intensity while the storms are becoming shorter in duration. So shorter storms, higher intensity, but the rainfall amounts are not substantively changing. So some interesting things going on there, some nuances that are taking place, which are not inconsistent with what a lot of the modeling efforts are suggesting might happen with the rainfall climatology in this region. Another study that, this is the last one I'm going to show you, and then I'll shut up for a while and try to entertain any questions you guys might have. But this is, in fact, I got invited to the CASC meeting for the Southeastern region. I think it was this past November or December. And I got teamed up with a group of ecologists from all across the Southeast. And we're working on a manuscript on the tropicalization of the temperate zone in the United States. And of course, everybody I was working with were ecologists, all focused on a certain organism, and they wanted a climate person to come in and talk a little bit about the climate. So I put together just a little cross section of 4 locations in this temperate zone, starting from the West Coast with San Francisco, moving eastward to Tucson, to New Orleans, and then to Tampa. Kind of creating sort of a west to east cross section, and looking at the green line represents the average winter temperatures for each of the 4 locations. The blue line represents the extreme single minimum temperature experienced each winter season at each of the 4 locations. And then the bottom bar graph are the number of freeze events. And in most cases, what we found was that the winter temperatures are increasing significantly. The minimum temperatures are becoming, the single extreme minimum temperature is becoming milder over time. Very noticeable here at San Francisco. And then the number of freezes is actually declining with time. And just using, I mean, you can kind of see that at all 4 locations. It's probably most dramatic at San Francisco. And what we have in San Francisco, we had, we had 17 events in alone, 17 days, individual days in the year 1940, the winter of 1949 alone. And you can notice that in the first half of this time series, most years have some number of freeze days, some of them being 10 or 11 and so on and so forth. But we've only had 15 freeze days since 1981. So starting here forward, we've only had a grand total of 15. We've had 5 freeze days since 1991, and only 1 since 2000 and 0 since 2008. So from this point forward, we haven't had a freeze at San Francisco. And notice how common they were in the earlier portion of this record. You can see, similar kinds of results at Tucson. I mean, they don't disappear completely, but there is a downward trend. It does represent a significant trend. In fact, I believe all 4 of these had significant downward trends in the total number of freeze days over this duration. So some interesting things happening there in terms of freezes across that temperate zone. So with that, I'm going to go ahead and stop. And I know I threw a lot of things at you. I sort of get a little bit of buckshot on some of the projects that we're working on, but I would gladly entertain questions on any of these topics.